All right, let's continue on with operations with radical expressions today. One key term we've got to know going into this lesson is what like radicals are. Again, you can find this definition on page 716. Put it into my own words here. Two expressions that have the same radicand. We would call those like radicals. And you've probably heard of like fractions before and like terms before. It's very similar. Only like fractions can be added and subtracted. Only like terms can be combined. Only like radicals can be combined. So let's simplify these two expressions, making sure that we simplify completely and only combine like radicals. Now in example A, all three of these terms are like radicals. They all have the square root of 7. So you can add these in any order you want. I like to add the positives first. And then that's 0 times the square root of 7, which is 0. Again, if you went 3 minus 5 is negative 2, and then negative 2 plus 2, you're still going to get 0 times the square root of 7, which is 0. Addition is commutative. You can do it in any order you want, so you're going to get to 0 no matter how you do this. Now in the second one here, we do not have like radicals, so we can't combine these. However, the square root of 125 can be simplified. We learned how to do this in chapter 9. Square root of 125 is like the square root of 25 times 5, 25 being a perfect square. So in other words, the square root of 125 can be rewritten as 5 times the square root of 5. Now we do have like radicals, and we can add them together. So this is 13 times the square root of 5. Okay, so they weren't like the radicals to begin with, but after I simplified, they were. Okay, now this is multiplying radicals, which we've actually done before back in chapter 9. If you have two terms and they're both inside a radicand, then you can multiply them together. So the square root of 12 times the square root of 3 can be rewritten as the square root of 36. And 36 is a perfect square, so we'll just simplify that. Again, that's review. You've done that before. Down here on part B, we've got a distributive property situation. We can distribute a radical just like we distribute a variable or just like we distribute any other real number. So we'll do the square root of 3 times 7, and we'll do the square root of 3 times the square root of 5. Square root of 3 times 7 is 7 square root of 3. And square root of 3 times square root of 5 is square root of 15. Over here, you always write the number first and then the radical second. Now, these are not like terms. Neither one of these radicals can be simplified, so we can't combine them. In other words, we're done. However, if you could simplify the radical, then do that and keep going. All right, again, we're multiplying some more, but we've got some radical expressions. This is 1 minus 3, or 1 minus the square root of 3 squared, which could also be stated as 1 minus the square root of 3 times 1 minus the square root of 3. I'm noticing, however, that this fits the square of a binomial pattern. So just like, if we had a variable here, this same pattern applies. So if we're doing one number minus another number and we're squaring that quantity, this pattern should be held true. So we should just be able to take a and square it. In other words, 1 squared, which is 1. And then in the middle, you've got double the product of the two terms. 1 times the square root of 3, or negative square root of 3, is negative square root of 3. Doubled would be negative 2 times the square root of 3. And then lastly, we should be able to square the second term. So square root of 3 times the square root of 3 is 3. Or even if you look at it as negative square root of 3 times negative square root of 3, it's still just 3. And square root of 3 times square root of 3 is the square root of 9, which is 3. Okay, now we have some like terms, 1 and 3, and we can add those together. However, these are not like radicals, so they cannot be combined. We're done. Okay, on part D, I'm noticing that I have a sum and difference pattern. A minus b times a plus b. So that should be a squared minus b squared. And again, we learned these in chapter 10. Now we're just doing them with radicals. So to simplify this, the shortcut would be to square the 6 and square the square root of 2. So 6 squared is 36. And then it's always going to be minus. And then square root of 2 squared, square root of 2 times the square root of 2 is the square root of 4, which is 2. And then those are obviously like terms. 36 minus 2 is 34. So we started off with radicals in our expression, but actually after we simplify this, the radicals are gone. An important thing that we want to notice when we're doing the next problem. Square root of 2 times the square root of 2 is 2. Square root of 2 squared. Remember, the middle terms would cancel out. 6 times the square root of 2 and negative 6 times the square root of 2. So those are gone. All right. So let's simplify this expression. We talked about this first one very, very little in section 1 of chapter 9. This is called rationalizing the denominator. And really what this should say is simplify up here. You cannot have a radical in the denominator of a fraction. So here's how we do that. It's called rationalizing the denominator. We'll just multiply by square root of 3 over square root of 3. When you multiply by 1, and that's what this number is, you don't change the value of the expression at all. So we're allowed to do that. Now 1 times the square root of 3 is the square root of 3, and the square root of 3 times the square root of 3 is the square root of 9, or 3. Now we don't have a radical in the denominator, and everything's simplified on top. That's our answer. You can't have radicals in the denominator of a fraction. We got the same issue here on part B. We can't have radicals in the denominator of this fraction. So how are we going to get rid of that? Well, look back at part D of example 2. If we use the sum and difference pattern, we should be able to eliminate radicals. So 3 plus square root of 2 times 3 minus the square root of 2 should eliminate radicals. On the top, we need to distribute. 4 times 3 is 12. And 4 times negative square root of 2 is 4 times, or is negative 4 square root of 2. On the bottom, we've got an a squared minus b squared situation. So a squared, 3 squared, is 9. And b squared, square root of 2 squared, is 2. A squared minus b squared. So we just simplify on the bottom. And we're done. There might be more simplifying you have to do. If all three of these terms had a common factor, you would want to divide that common factor out of them, but not possible here. Okay, last one. Is this radical expression a solution of this equation? Well, there's a hard way and an easy way to do this. Here's the hard way. We're going to plug that expression into the original equation. So there's x squared plus 5 times x minus 2. And that should equal 0 if that is a solution. Now over here, what I'm doing is squaring that binomial. So square of a binomial pattern should be a squared. Negative 5 times negative 5 is 25. In the middle, you've got their product. Negative 5 times negative square root of 33 is 5 square root of 33. Doubled is 10 square root of 33. And over here, we've got negative square root of 33 squared, which is just 33. On the bottom, 2 squared is 4. Next term, we have to multiply. 5 times negative 5 is negative 25. 5 times negative square root of 33 is negative 5 square root of 33. Write out the rest of the equation. Now, to add these three terms, I need to get a common denominator. I'll use 4. So obviously to turn 2 into something with 4 on the bottom, you'd multiply by 4 over 4, get 8 over 4. On this, we're going to multiply by 2 over 2. 2 times 2 is 4. 2 times this quantity is this quantity. 2 times negative 25 is negative 50. 2 times negative 5 square root of 33 is negative 10 square root of 33. Now we've got common denominators. Combine like terms in the numerators. 25 plus 33 is 58. Plus a negative 50 is 8. Plus a negative 8 is 0. 10 square root of 33 plus negative 10 square root of 33 is also 0. Everything is canceled out on top. So we have 0 over the square root of 4 equals 0, which of course is 0 equals 0, meaning negative 5 minus the square root of 3 over 2 is a solution to this equation. All right, so we'll pull out our graphing calculator here and try and do it an easier way. I'm going to take this expression, negative 5 minus the square root of 33 divided by 2, and I'm going to store it as x. Then I'm going to take this equation, or this left side of the equation anyway, type that in, x squared plus 5x minus 2. And if this expression, negative 5 minus the square root of 33 divided by 2, is a solution, then this expression should equal 0. It does. Okay. Another way would be to graph it. So we could do x squared plus 5x minus 2 and graph it and look for where it crosses the x-axis. Then we could go trace. We could type in negative 5 minus the square root of 33 divided by 2, and we'll see that that hits the x-axis perfectly because y is 0. That's another way to tell it's a solution. So graphing calculator, definitely the easier route here. All right, so that's it for section 12.2. Rewatch anything you need to rewatch and come in tomorrow with your questions. Good luck.